Welcome back, grade 10s. In today's lesson, we are going to continue learning about longitudinal waves. Now, when it comes to sound waves, remember that sound waves are all transmitted by means of longitudinal waves. The sound source creates vibrations in the air particles, and as they move forward, they push against neighboring particles. But then they have to move back due to diffusion to their original position. And this creates compressions and rarefactions. Remember that compressions are regions of high pressure, while rarefactions are regions of low pressure. Now, the medium through which sound waves travel will include gases, liquids, and solids. Obviously, when we talk, the medium through which people can hear us is the air. But sound doesn't only travel through gases, it also travels through liquids and solids. And in fact, it travels even more efficiently through liquids and solids. So that brings us to the speed of sound. The speed of sound depends on the properties of the medium. So remember that the speed of a wave depends only on the medium through which it travels. So the speed of a sound wave depends on the medium through which it travels, and different mediums have different densities and different temperatures, which would then impact the speed of sound of that wave. Sound travels faster in mediums that are more dense, like solids. And the reason for that is that the particles are closer together. Remember that sound waves are caused by vibrations in the medium, meaning that the particles carry that energy. And in a solid, the particles are so close together, and those vibrations are then able to transfer that energy more efficiently without losing energy in the process. In contrast, sound travels slower in mediums that are less dense, like gases, because the particles are further apart. So therefore, the particles need to transmit that energy to the next set of particles, which are quite a lot further away from them relative to the solid state. So due to the closeness of the particles in denser mediums, it makes sense that sound would travel faster in denser mediums. Sound also travels further in denser mediums, meaning that if you generate the same sound in air as you do through a solid, then the sound will travel further, the same sound will travel further in the solid matter. And that's, again, because the particles are so tightly packed together that it preserves the energy of the vibration, so less energy is lost over distances, which is why that sound travels further. Now, this is a table that shows the speed of sound through different mediums. You do not need to memorize this. For a given question, you will be given the speed of sound through that medium. But we can see that the speed of sound through air is about 330, 340 degrees Celsius, depending on the temperature. Then in seawater, it is about 5 times the speed. And over here, when we look at different solids, depending on their densities, the speed varies, but we can see that through solids, the speed of sound is much higher than it is in gases or in liquids. So the speed of sound in air at 0 degrees Celsius is 331 meters per second, and this value should be given to you on a formula sheet. The speed of sound in air at 20 degrees Celsius is 343 meters per second. Now remember that what we said is that denser mediums transfer that energy, that sound wave, better than less dense mediums. At 0 degrees Celsius, air particles are more dense than at 20 degrees Celsius. But then why is it that at 20 degrees Celsius, the speed of sound through air is actually faster? So that applies to a particular medium. If we increase the temperature of a specific medium, then the speed of sound will increase. And that's because in a warmer medium, the particles that make up that medium have more kinetic energy. They move and they vibrate faster, and that enables the sound wave to propagate faster in a warmer medium. So remember that the speed of sound in air is about 331 meters per second on a 0 degree Celsius day, but the speed of light through vacuum and air, what's also a constant value, is 3 times 10 to the 8 meters per second. That is the value given to you on the formula sheet, which is the same as 300 million meters per second. So while sound travels at about 330 meters in 1 second, light travels at 300 million meters in 1 second. So which one is traveling faster? Well, the speed of light is about 1,000,000 times faster than the speed of sound. The implication of this is therefore that sound travels much slower than light through air and other mediums. And this fact was identified when cannons were first used. When people looked at a firing cannon from a distance, they saw the flash of the cannon before they heard the bang of the cannon. We experience the same thing during a thunderstorm. We see the lightning flash, and only a little later do we hear the sound of the thunder. This is called the flash and bang method, and the flash and bang method allows us to calculate the speed of sound in air. And we may also use the flash and bang method to identify the distance from us to the sound source. What's important to remember is that if you're standing right next to the cannon, the light and the sound are actually generated at the same time by the same object. But the question is, how long does it take the light to reach our eyes? Well, that's very, very quick. But how long does it take the sound to reach our ears? Well, that would take longer. And when we're standing really close to the cannon, our brains can't identify that time difference, that time lapse between the speed of sound and the speed of light. But the further you are from the source, the more apparent this becomes, where the light gets to you a lot sooner than the sound does. Now recall that the equation for speed is distance over time. The distance is measured in meters, and it's the distance from the source of the sound to the receiver, such as the person that is picking up the sound. The time is how long does it take for the sound to reach the ear after seeing the flash, measured in seconds. And the speed would then be the speed of the sound through that medium, measured in meters per second. Let's talk about the reflection of sound waves and echoes. When a sound wave hits a surface, some of it gets absorbed by the surface, some of it gets transmitted, meaning that it moves through the surface, and some of it gets reflected off the surface. The absorbed sound waves get converted into heat energy. The transmitted sound waves will be heard in the next room or behind the object. Now, generally speaking, when it comes to sound wave, we look for soundproof walls to minimize transmission. The rest of the sound waves get reflected back into the room. Now, when you have a room filled with objects, the objects absorb most of that sound energy. And this reduces the amount of sound energy that reflects back. And it's the reflected waves that get reflected back into the ear. Now, over and above that, the reflected sound waves get scattered in many different directions. That's when there are a lot of objects in the room. So the sound waves will hit the objects and reflect off. But because there are so many objects, they hit the objects at different angles and get reflected off at those same angles. So we end up creating overlaps and a complex sound field that our brain cannot identify as an echo. However, when there is a large and open space with a hard surface, a hard reflecting surface like a wall or a cliff, then the reflected sound waves will enter the ear in such a way that the reflected waves look the same as the original waves. They haven't been reflected off at different angles, they haven't scattered in different directions. They maintain the same sound wave but in the opposite direction, traveling into your ear. For an echo to be distinct and perceptible to the human ear, it needs to be separated in time from the original sound wave by at least 50 milliseconds, and that corresponds to 17 meters between the source of the sound and the reflective surface. So if the distance here is 17 meters, then a distinct echo will be heard. Sometimes we hear what we call an echo, but it's not a distinct returning sound waves, and that's actually called a reverberation. Sonar technology uses sound waves to detect and locate objects underwater. Sonar stands for sound navigation and ranging. And the way that this system works is by emitting sound waves from a transmitter and then listening for the echoes that reflect back from the surrounding objects. Sonar technology is used to identify the depth of the ocean floor, to detect or track underwater objects like ships and submarines and marine life, and in search and rescue operations. Animals like bats and dolphins, they make use of echolocation. That is just like the sonar technology, but it's a biological sonar system that allows certain animals to navigate and locate objects in their environment. And they do this by emitting high-frequency sound waves, known as ultrasound, which we'll discuss shortly, and then they listen to the echoes that reflect back. Now, based on the echoes that reflect back into the animal's ear, the animal can gain information about the object, such as location, size, shape, and texture. The animal's brain uses this information and it creates a map of its environment, and it helps the animal to navigate its surroundings, locate prey and predators and other objects. Now we're going to move on to some examples. All of these examples are questions that apply to the flash and bang method, to echoes, and to sonar technology. Now, for those three types of questions, flash and bang, echoes, and sonar, we do not use the wave formula. So we don't say that the wave speed is equal to the wavelength divided by the period or the wavelength times the frequency. We use the original formula of speed equals distance over time. So let's take a look at some examples. The distance between 2 points is 0.5 kilometers. The average time between seeing the flash and hearing the sound is 1.5 seconds. Calculate the speed of the sound. So remember that we may not work in kilometers, so we upfront have to convert our kilometers into meters. So seeing kilometers here should immediately set off alarm bells in your heads. And the time is given to us in seconds, so we're happy with that. We're going to use the formula of speed equals distance over time because this question applies to the flash and bang method. We are trying to figure out the speed of the sound given the distance and given the time. So it's 0.5 times 10 to the 3 meters divided by 1.5 seconds. And we get a speed of sound of 333.33 meters per second. Often on a test, this will be followed up by a question asking if this means that the sound is being transmitted through air. And remember that the speed of sound through air, depending on the temperature, would be around 330 to 350 meters per second. So this is definitely in line with the speed of sound in air. A lightning storm creates both lightning and thunder. You see the lightning almost immediately because light travels so fast at 3 times 10 to the 8 meters per second. But after seeing the lightning, you count 4 seconds and then you hear the thunder. So what is the distance from you to the location of the storm, assuming that the speed of sound is 340 meters per second? Provide your final answer in kilometers. Now you are going to get automatically your final answer into meters. Under normal circumstances, you leave it in meters unless stated otherwise, and in this case, they'd like us to convert the final answer into kilometers. So remember, we're going to use the formula speed equals distance over time because this question applies to the flash and bang method. However, we want to figure out the distance. So we may rearrange the formula as distance equals speed times time. We have the speed and we have the time, 340 times 4, and we get an answer of 1,360 meters. That means that that is the distance from you to the storm if you've counted 4 seconds from the time that you saw the lightning to the time that you heard the thunder. We have to convert our final answer into kilometers. So from meters to kilometers, we multiply by 10 to the minus 3. You can also say 1.36 kilometers. The person is yelling from a second-story window to another person standing at the garden gate 50 meters away. If the speed of sound is 344 meters per second, how long does it take the sound to reach the person standing at the gate? Your answer is automatically going to be in seconds, but we were asked to convert it into milliseconds. So the formula is speed equals distance over time, but we want to work out the time, so we may rearrange this formula as time equals distance over speed. We have the distance and the speed. So it is 50 divided by 344, which gives us an answer of 0.145 seconds. And we need to convert that into milliseconds. So from a second to a millisecond, we multiply by 10 to the 3. So it's 0.145 times 10 to the 3 milliseconds. A ship sends a signal to the bottom of the ocean to determine the depth of the ocean. The speed of sound in seawater is 1,450 meters per second. If the signal is received 1.5 seconds later, How deep is the ocean at that point? Provide your final answer in kilometers. Now, take a look at this hint. The sound wave travels to the bottom of the ocean and back in 1.5 seconds. This is something that we need to be cognizant of when it comes to questions around sonar and also often around echoes. So if we consider these two diagrams, remember that if the transmitter is sending a sound wave to the bottom of the ocean, and then the transmitter picks up that sound wave again in that same location. Now, in this case, it takes 1.5 seconds for the sound wave to get to the bottom of the ocean and back to the transmitter, which is also a receiver. So the bottom of the ocean, that distance would not be based on the full 1.5 seconds, but rather half that time, because how long would it take the sound wave to reach the bottom of the ocean? Half of this amount of time. And in many echo questions, we also have to take into account that the sound hits the wall and then reflects back into the ear. So in this question, the time for the signal to reach the bottom of the ocean is 1.5 divided by 2, which is 0.75 seconds. And we need to do this up front because that is logical. So now we can say speed equals distance over time. What we're trying to work out, though, is the distance, which we may rearrange as speed times time. We have the speed of sound in seawater, and we know how long it took the sound wave to reach the bottom of the ocean or the ocean floor. So that's 1450 times 0.75, and so the distance from the ship to the ocean floor is 1087.5 meters, which we need to convert into kilometers. So it's 1087.5 times 10 to the minus 3 kilometers.